Hi everyone, so in this video we're going to talk about section 1.3 of the notes, which is the properties of the integers. How can we deduce the properties of the integers from the axioms? So just to remind you, in chapter 0, and in our first class, we talked about some of the properties of the integers, including the properties of addition. So this included substitution law, the commutativity, associativity, the existence of the additive identity and of inverses and similar things for multiplication. And then there was I mentioned the distributive law, which connects the addition and multiplication. There are some other important properties of the integers, the axioms, which is one of them. One group of those is called trichotomy axioms or trichotomy principle, which says that the integers are divided into three groups: positive integers, 0, and negative integers, and positive integers are also called natural numbers. And so other important axioms include the positivity axiom and a well-ordering property of n. So for instance, the well-ordering says that any non-empty subset of the natural numbers has a smallest element. So based on these axioms, there's properties of the integers which we use all the time, but we haven't, a lot of the times we don't really think much about those. So today we're going to deduce some of these properties of the integers starting from the axioms we mentioned before. So some of these include the subtraction equality principle, which says that x equals y if and only if x minus y equals 0, and several other ones. And I won't be able to cover all of them, but I'll give you an idea how you can write down the proof, at least in some of these situations, some of the important situations. Okay, so let's start with one of the important properties of the integers, which is called the subtraction equality principle, which says that for all integers x and y, you have that x is equal to y if and only if x minus y is equal to 0. So remember, 0 was the additive identity. So there is so we want to see why this property is true. So first of all, before we start talking about proof of this particular example, I want to mention there is really two styles of proofs. So here I read there is two styles of proofs which are often used, and one of them is the one we will do for this problem is called the column method. So we have a statement next to it, we write the reason that statement is true, and another one is what's called the text method. So we write in plain sentences using the laws of regular grammar. So you can read in the text that most of the time we will be using the regular proofs when we write regular sentences, but in this situation, so sometimes it's also very easy and useful to write the proofs in terms of this two-column style, which I will be doing it right now. Okay, so let's try to show that we have this property that x minus y equals 0 if and only if x equals y. So to start with, we should know that really there is two statements we need to show. One of them is if you have the left-hand side implies the right-hand side. So this is often denoted like this, right? So we have one of the implications, and in the other implication, the right-hand side implies the left-hand side. So we would write it like this. So first, let's start by showing that the left-hand side implies the right-hand side. So I'll just denote the shorthand notation for that will be just we'll be doing this part of the proof, right? So if you have x minus y equals 0, then x equals y. So our assumption is that x minus y is equal to 0. So using the fact what's called the substitution axiom, if we add both sides of this equality y, then we will get what? X minus y, right, plus y equals 0 plus y. Note that we cannot right now just write for the right hand side that 0 plus y is equal to y. Well, let's just, because we don't even, I mean, it follows from the axioms, but we have to write which axiom we're using at each step. So this particular one is the substitution law, which says that if you have two things, if you remember the substitution law said that if you have A equals B and C equals D, then A plus C equals B plus D. And in this case, we have that x minus y, which could be our A, is equal to 0, which could be our B, and then C and D could be y on both cases. So this is saying that this part is equal to that, this part is equal to that. So when you add them up, you get the same things. Okay, now how can I get from this to x equals y? Well, first of all, I would have to use the associative law by writing that, well, actually, the definition of subtraction, that x minus y is nothing else but x plus minus y, right? And then I have plus y, that's equal to 0 plus y. This is by the definition of subtraction, right? Because saying that I'm I'm subtracting y is the same as I'm adding minus y. So then I can write x plus minus y plus y. Well, how can I do that? Why is that true? Well, that's true because I use the associativity. So let me just write addition is associative, right? So I use that to say that, well, if I have three integers, then I can write a plus b plus c is equal to a plus, in parentheses, b plus c, okay? So then now by the axiom of the inverse, I have that x plus y plus 0, because this part here is equal to 0, is equal to 0 plus y, right? So I used here the existence of the inverses. Additive inverse, right? what does it say? It says that if you take the inverse, which is actually negative y, and you add to y, then you always get the additive inverse back. And now, by the fact that I have commutativity, I can write that I have this is equal to 0 plus x is equal to 0 plus y. So we're using commutativity. Actually, here we could have said that by the we could have just immediately said that this implies that x is equal to y by the axiom of the identity, right? So additive identity. So if you remember, the axiom of additive identity says that 0 is the additive identity, meaning that x plus 0 is equal to x for every x, and 0 plus y is equal to y. So that's how we get one of the directions of what we want. So this is just to illustrate how you can show this cancellation, the subtraction equality principle just from the axioms um, of the integers, and then we can do the other direction. So let me actually, so we want to show, actually, let's do it like this. So I want to go now in the opposite direction here. I want to say that if x equals y, then x minus y is equal to 0. So this is again our assumption. So the idea would be to subtract y from both sides. What does that mean? That means you have to add negative y to both sides. So then I'm going to write x plus minus y equals y plus minus y. Again, this follows from the substitution law, right? Substitution. Right? So what does that mean? That means because x equals y, and well, negative y is equal to negative y, so I can add this both sides and I get the same answer. But this thing here is just the by definition of the subtraction. This is just x minus y, and by the axiom for the inverses, this is equal to 0. So this is equal to 0. So the left-hand side by definition of subtraction, and by the identity, actually, additive inverse axiom, right? So the additive inverse says that if you take y, you add to negative y to that, you always get the additive identity. And that's all. So whenever you write the proof, you can say that this finishes the proof, or you can write QED, or you can just put the box like that at the end, and that would be the end of your proof. Okay. So the next video will give you another example where we can prove a property of integers from the axioms.